For this chapter, we're going to be talking about neurons. Let's first begin with electrical potential and what that means. Electrical potential is a difference in the charge between two areas. So from this picture, it's showing you that there's a plasma membrane down here. So this is the plasma membrane, and that there are a slight negative charge within the plasma membrane. So this is the cytosol or the cytoplasm here. However, outside the plasma membrane, it's slightly positive. And we talked about this before, where inside the cell it tends to be slightly negative, and we'll go into the reasons why in just a second. But this electrical potential is showing you that there is a positive charge on the outside of the cell and a negative charge on the inside of the cell. And when we talk about specific electrical potential, this membrane potential, this is that electrical potential across the plasma membrane itself. So this is an example of electrical potential, but it's specifically talking about around the plasma membrane, which I kind of drew on this picture here. Typically speaking, in neurons, we have a resting membrane potential of negative 70 millivolts, meaning that within the cell, it's slightly negative, so negative 70 millivolts within the cell. And then outside of the cell, it's going to be positive outside. Okay, so it's negative 70 millivolts within the cell. And you'll need to know this number when you go into physiology. So this membrane potential, like we said, for neurons, is negative 70 millivolts within the cell, is this difference in the charge across the plasma membrane with the negative on the inside. And we just talked about how inside the cell, or intracellular, is slightly negative compared to extracellular. Extracellular means outside of the cell. And partially the reasons why is because of this pump called the sodium-potassium pump. The sodium-potassium pump, it's going to end up pumping 3 sodium ions out of the cell and 2 potassium into the cell. If you look at this, the net amount of positive charges is that there's going to be one positive charge that's going to go out of the cell. If there's one positive charge going out of the cell, that means that inside the cell is going to be a little bit more negative. Certain proteins, ATP and nucleic acids, are all anions. Regarding to ATP, this is adenosine triphosphate. And phosphates in general are negatively charged ions. And nucleic acids also has phosphate backbones, and those phosphate backbones will be negatively charged. And because of all those ATP and DNA and RNA and also other proteins, that will end up causing the cell inside to be slightly negative. And because of these things, this is going to cause this membrane potential to be slightly negative on the inside. When we end up measuring the voltage change across the cell, there will be this difference due to the concentration gradient of the ions. We'll later learn about which ions are greater where, and also how permeable these ions are across the membrane. Some are more permeable than others. Permeable means how easily it could go across the plasma membrane. And out of all the ions that we're going to be learning, potassium is the most permeable. Remember, permeable is how easy it could go across the plasma membrane. The potassium is the easiest to cross the plasma membrane. And since potassium is a positively charged ion, and we just said earlier on that inside the cell is slightly negative, so this being positive, it's going to want to go into the cell due to the negative charge of the cell within the cell. And so that's why we have more potassium inside the cell than outside of the cell. And so it has a higher concentration of potassium intracellularly. So here is showing you that the different ions and where they're concentrated at. Once again, the resting membrane potential of a neuron is negative 70 millivolts. And generally speaking, potassium, we just said, is going to be more on the inside compared to on the outside. So these brackets are to show you the concentration. So this is the concentration of potassium inside the cell is greater than the potassium concentration outside of the cell. And if you look at these numbers here, this is showing you those numbers. It'll show you that extracellularly, so outside of the cell, we only have 5 millimolars of potassium. However, within the cell, we have 150 millimolars of potassium. For sodium, we have more on the outside of the cell compared to the inside of the cell. So over here, sodium is 145 millimolars outside of the cell extracellularly, but only 15 millimolars intracellularly. Calcium, also more on the outside compared to the inside. 108 millimolars of calcium on the outside and only 10 millimolars on the inside of the cell. And lastly, chloride. Chloride is also more on the outside compared to the inside. So here, only 1 millimolar extracellularly, but only 0.0001 millimolars intracellularly. So out of all these, you could see that the only one that has more on the inside of the cell that we need to know is potassium. Potassium is more concentrated on the inside compared to the outside. I don't know if you know this, but things like to go from higher concentration to lower concentration, meaning that if there is some kind of channel or some kind of protein that will allow these ions to pass across the plasma membrane, the ions will want to go from higher concentration to lower concentration. So for example, if we talk about potassium here, we just mentioned that it's more concentrated on the inside compared to the outside here. So if there was a channel that opens, potassium will want to go from in to out of the cell. So potassium will be going out of the cell, generally speaking. However, for sodium, it's more concentrated on the outside, so it will want to go into the cell. So eventually, if there's a channel that opens for sodium, most of it is going to go into the cell. Same thing with calcium. Calcium is more greater on the outside, so it will want to go into the cell. And chloride as well. Chloride being greater on the outside will also want to go into the cell. Here's some terminology that we want to know as well. We just mentioned about resting membrane potential. And resting membrane potential, this is when the cell is at rest. Meaning that the cell is not excited by anything. This is the normal charge within the cell. And we said normally it's going to be negatively charged. And in a neuron, it's going to be negative 70 millivolts, as you can see over here. It's negative 70 millivolts. So due to this is when it's at rest. When it does get somewhat excited, this is called depolarization. And when it gets depolarized, it becomes more and more positive. As you can see from this graph over here, this is the membrane potential. I'm going to just abbreviate it as a mempot. And this is showing you as it's increasing in positivity, this is going to be called depolarization. However, if we're going to become going back to resting membrane potential, this is called repolarization. So it becomes more negative, but not below resting membrane potential. So it only goes up to resting membrane potential. If we go even further than resting membrane potential, this is going to be called hyperpolarization. when it becomes more negative than the resting membrane potential. There is this term called threshold, and this threshold for a neuron is going to be this negative 55 millivolts for a neuron. What this means is that if we depolarize the cell to threshold, it's going to become excited. And when it becomes excited, it's going to cause what we call an action potential. So this part here shows you its resting membrane potential at negative 70 millivolts. And then we depolarize it, making it more positive until we get to negative 55 millivolts. And that's threshold. Once it hits that negative 55 millivolts, then it's going to cause this thing called an action potential to occur. Next, we'll be talking about graded potential, but we'll cover that next time.